Hello everyone, welcome once again to this series of lecture video on unsupervised learning. My name is Priscilla Chamenyi. I am a junior data scientist for global communities in the Laboratory of Data Science. In the last video, we took a look at GMMs. Today, we'll be talking in depth about the EM algorithm used in GMM. Let's dive in. So the expectation maximization algorithm, the EM algorithm, is used for obtaining maximum likelihood estimates of parameters when some of the data is missing. More generally, it can also be applied when there is latent, that is, an unobserved data which was never intended to be observed. It serves as the foundation for many unsupervised classroom algorithms in the field of machine learning. How does this algorithm work? Now, this algorithm, as we have already stated in the last video, consists of two steps. That's an estimation step, also known as the E step, and a maximization step, the M step, forming an iterative process to improve model fit. In the E step, the algorithm calculates the expected values of the latent variables by computing the expectation of the log likelihood based on the current parameter. In the M step, it identifies the parameter that maximizes the expected log likelihood calculated during the E step, updating the model parameters based on the estimated latent variables. Now, these two steps are iterated repeatedly until the algorithm has been able to maximize the likelihood of the observed data. Now, we've mentioned some words like latent variables, likelihood, log likelihood in the definitions and how the algorithm works. So we want to take a look at how these common terms are explained. So for latent variables are unobserved variables in statistical models that can only be inferred indirectly through their effects on observable variables. Likelihood is the probability of observing the given data given the parameters of the model. Log likelihood is the logarithm of the likelihood function, which measures the goodness of fit between the observed data and the model. Maximum likelihood estimation, MLE, is a method to estimate the parameters of a statistical model by finding the parameter values that maximize their likelihood function. The MLE measures how well the model explains the observed data. Now, we know that our algorithm is supposed to converge, so we want to explain what convergence means. Now, this refers to the condition when the EM algorithm has reached a stable solution. Convergence in this case is determined by checking if the change in the log likelihood or the parameter estimate falls below a predefined threshold. So this is the steps the algorithm follows. It starts, we're going to look at the step-by-step process the algorithm follows. And this is a diagram that better explains these steps. So first, there's an initialization, where a set of initial parameter value is chosen. The system is provided with incomplete observed data, assuming that the data originates from a specific model. After we are done with initialization, we move to the E step. That's the expectation step. In this step, the responsibility of each latent variable is computed given the observed data and the current parameter estimates. Then, Missing or incomplete data values are estimated, and then the log likelihood of the observed data is computed based on the current parameter estimates and estimated missing data. The next step is the M step. In this step, we update the model parameters by maximizing the expected complete data log likelihood calculated in this step. This involves solving optimization problems to find parameter values that maximize the log likelihood. The chosen optimization technique is dependent on the specific problem and model at hand. And now our last step is the convergence step. And in this step, we check for convergence by comparing the change in log likelihood or the parameter values between iterations. If the change is below a predefined threshold, we stop and consider the algorithm has converged. Otherwise, we go back to the E step and repeat the process until we achieve convergence. Here are some of the advantages of the EM algorithm. The EM algorithm can estimate missing values using observed data and the model structure. It is suitable for large data sets and complex models. It is also useful for unsupervised learning tasks such as clustering and density estimation. And lastly, it provides direction for parameter estimation, leading to local maxima of the likelihood function. Some of its disadvantages are that convergence and results can be impacted by the choice of initial parameters. It can also be slow to converge, especially for large datasets or complex models. The algorithm assumes that the data is generated from a specific statistical model, which may not always be the case. And then lastly, implementing the algorithm correctly can be complex, especially for some applications. This brings us to the end of today's video. This work is brought to you by the Laboratory of Data Science in the Indiana Data Mine Grant, and it is supervised by Professor Alessandro Selvitella. Till we meet again, bye and thank you.